Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
All right, welcome back everyone to week 4. Today, we're going to dive into what I think is one of the most exciting stories in the history of AI. I like to call it the Cambrian explosion of deep learning. Just like in biology, this was a period where, after a long time of things being pretty quiet, suddenly there was this burst of creativity, complexity, and diversification in neural networks. We're going to trace the evolution of CNNs from their early, almost forgotten academic roots to the models that really built the foundations of modern computer vision. So here's our game plan. We'll start with a period I'm calling the Great Stagnation to understand why progress stalled for so long. Then we'll look at the perfect storm of events in 2012 that changed everything. After that, we're going to tear down AlexNet, the network that started the revolution, and see what made it tick. Then we'll explore the VGG philosophy, which is all about standardization and simplicity. And we'll wrap it all up by looking at the cost, the performance, and the big question these models left us with. Okay, so let's get into it. You might think the story of modern deep learning starts with a huge bang, but it's actually the opposite. It starts with a long, quiet period of dormancy. After LeNet 5 came out in 1998, and it was a huge deal for its time, the field just went quiet. The basic ideas were there, but they were trapped, held back by some really serious mathematical and computational walls. This timeline really puts it into perspective. See that giant gap? In 1998, Jan LeCun gives us LeNet 5, and it was fantastic for recognizing handwritten digits. But then, for more than a decade, nothing. The rest of the computer vision world basically moved on. People were focused on more classical methods like support vector machines and handcrafted features like SIFT and HOG, because frankly, deep networks just couldn't scale up to solve bigger problems. It wasn't until 2012 that everything changed, kicking off what we now call the deep learning renaissance. So, what was the problem? Why the big stall? Well, a major issue was a fundamental capacity mismatch. Just look at this slide. On the left, you have the LeNet 5 architecture. It's relatively shallow, it's simple, and it was designed to handle these tiny 28 by 28 pixel black and white images of numbers. On the right, you have the kind of image you'd find in the ImageNet dataset. High resolution, complex, full of textures and shapes. LeNet 5 just didn't have the depth or the capacity to learn the kinds of hierarchical features you need to tell the difference between 1,000 different kinds of objects. The model was simply too small for the job. But the deeper, more sinister problem, the one that really built a mathematical wall, was the vanishing gradient. Early networks all relied on the sigmoid activation function, and its fatal flaw is right here in its derivative. Look at that graph. The absolute maximum value it can ever have is a tiny 0.25. Now, during backpropagation, you use the chain rule, which means you're multiplying these derivatives together, layer after layer. When you keep multiplying numbers that are less than 1, the result just plummets towards 0. For deep networks, this meant the error signal from the output would completely evaporate by the time it got to the early layers, so those layers couldn't learn anything at all. Okay, so with these huge roadblocks, how did things finally break loose in 2012? It wasn't one single eureka moment. It was more like a perfect storm. A convergence of 3 critical and mostly independent factors that all came together at exactly the right time to create the perfect conditions for a revolution. And this Venn diagram shows those 3 pillars perfectly. Think of it like a recipe. First, you need a massive amount of data scale. That's your fuel. Second, you need powerful parallel compute. That's your engine. And third, you need some clever new algorithms. That's the spark. Before 2012, the field might have had 1 or 2 of these pieces, but never all 3 at the same time. It was the intersection of all 3 that made the breakthrough almost inevitable. So let's talk about the fuel. Deep neural networks are incredibly data hungry. They're absolute monsters. LeNet was trained on the MNES dataset, which had around 60,000 images. But ImageNet, which came out a few years before 2012, was a total game changer. It gave researchers access to 1.2 million high-resolution labeled images across 1,000 different categories. That sheer scale was exactly what was needed to train these huge, deep models without them just memorizing the training data. Next, you need the engine, compute. Training these big networks is basically just doing an astronomical number of matrix multiplications. CPUs, which are designed to do things one at a time, are painfully slow at this. But then we had the rise of GPUs, graphics processing units. These were originally built for the gaming industry to render complex scenes, which meant they were designed to do tons of simple calculations in parallel. The moment people realized you could use GPUs for general-purpose computing, the GPU revolution was pivotal. A training run that would have taken months on a CPU can now be done in just a few days. And finally, you need the spark. Because you can have all the data and all the compute power in the world, but if you're still stuck with vanishing gradients, you're going nowhere. The spark came from two major algorithmic pivots. First, the simple but revolutionary switch from the sigmoid function to the rectified linear unit, or ReLU. And second, a clever new technique to prevent overfitting called dropout. These two innovations directly smashed through the mathematical bottlenecks that had been holding the field back for a decade. And all of this brings us to the hero of the story, AlexNet. This was the architecture developed by Alex Krizhevsky, Ilya Sudscover, and Jeff Hinton that put all three pieces together. At the 2012 ImageNet competition, AlexNet didn't just win, it completely shattered the previous records. It was a clear signal to the entire field that a new era of computer vision had officially begun. So let's pop the hood and take a look. AlexNet was an 8-layer network with roughly 60 million parameters, which was just unbelievably massive for its time. One of the first things you'll probably notice is its weird split GPU design. Now, this wasn't for some fancy theoretical reason, it was a practical necessity. The best GPUs you could get at the time, the NVIDIA GTX 580s, only had 3 gigabytes of video memory, not nearly enough to hold the entire model. So they literally had to split the network across 2 separate GPUs and get them to communicate during training. This clever hack allowed them to train a model that was bigger and deeper than anyone else could. So, how did AlexNet get around that killer vanishing gradient problem? By making a radical move. It completely ditched sigmoid and tang in the hidden layers and used the rectified linear unit, or ReLU, instead. And looking at this graph, the difference is just night and day. Sigmoid's gradient saturates, it flattens out, it dies. But ReLU, for any positive input, has a gradient that's a constant 1. It's non-saturating. This incredibly simple function, just max of 0 and x, finally allowed gradients to flow all the way from the end of the network back to the beginning, making it possible to actually train deep networks effectively. The second crucial innovation was dropout. With 60 million parameters, the risk of the model just memorizing the training data, overfitting, was enormous. Dropout is a brilliantly simple yet powerful solution. During each forward pass of training, you randomly drop out a fraction of the neurons, essentially setting their activations to 0. It's like you're training a different, thinned-out network at every single iteration. This prevents neurons from becoming too codependent on each other and forces them to learn more robust, independent features. It's an incredible trick, like training a huge ensemble of networks for the price of one. And to fight overfitting even more, AlexNet used data augmentation, and they used it heavily. They took the 1.2 million training images and artificially blew up the dataset by orders of magnitude. They would generate random crops, do horizontal flips, and mess with the color and lighting. What this does is it teaches the model the concept of semantic invariance, the idea that a cat is still a cat no matter where it is in the frame, how big it is, or what the lighting looks like. It's a critical technique that is still standard practice today for training any large model. Now, AlexNet was a monumental achievement, but its architecture was a bit bespoke. It had all these different kernel sizes and a complex structure. So the next great leap forward, which came out of the visual geometry group at Oxford in 2014, wasn't about some radical new invention. It was about a new philosophy, standardization and modularity. The core insight of the VGG network is beautiful in its simplicity. Instead of using a whole variety of large kernel sizes like AlexNet did with its 11 by 11 and 5 by 5 filters, the VGG architects decided to use only one size, tiny 3 by 3 convolutional kernels. Their entire design principle was just to stack these small kernels one after another, going deeper and deeper. And the counterintuitive result was a network that was not only deeper and more powerful, but also more parameter efficient. Now, to understand why this works so well, we need to quickly define a concept called the effective receptive field, or ERF. In simple terms, it's the area of the original input image that a particular neuron or a pixel in a feature map can see. A neuron in the first layer can only see a little 3 by 3 patch, but a neuron deeper in the network is looking at the output of the neurons below it, so its effective view of the original image gets much, much larger. This diagram of an expanding cone of visibility shows exactly how it works. Each 3x3 convolution you add operates on the feature map from the layer before it, which makes that effective receptive field bigger. For example, if you stack two 3x3 convolution layers, you get an effective receptive field of 5x5, the same as a single, larger 5x5 filter. If you stack three of them, you get a 7x7 receptive field. This strategy allows the network to build up a picture of the global context just by repeating a series of very simple local operations. And here's the crucial math that proves why this is so clever. Let's compare a single 5x5 convolution to two stacked 3x3 ones. They both achieve the exact same receptive field. But for the 5x5 layer, the number of parameters is proportional to 5 squared, which is 25. For the two 3x3 layers, it's 2 times 3 squared, which is only 18. That's a 28% reduction in parameters. On top of that, by stacking two layers, you get to apply two nonlinear ReLU activations instead of just one, which makes the model's decision-making more powerful. So the VGG approach is deeper, it has more nonlinearities, and it's cheaper on parameters. It's an elegant win-win. VGG's clean, modular design became the new standard. Its simplicity was its greatest strength. But, and this is a big but, that simplicity, that brute force approach of just stacking more and more layers, came at a staggering computational and memory cost, which we absolutely have to analyze. This chart tells the whole story. While VGG was more parameter efficient in its convolutional part, it was an absolute monster in its final fully connected layers. The first dense layer alone had over 100 million parameters. As a result, both its memory footprint and its computational cost, measured in flops, just skyrocketed compared to AlexNet. VGG proved that depth was the key to performance, but it achieved that depth by throwing an enormous amount of compute and memory at the problem. So let's just summarize this incredible evolutionary leap. We started with LeNet back in 1998, a great idea that was crippled by the math of vanishing gradients, leading to a decade of stagnation. Then came AlexNet in 2012, the spark that ignited the revolution by finally solving those core optimization problems with ReLU and dropout. And just 2 years later, VGG gave us a refinement, a standardized modular design that proved that just going deeper with simple, uniform blocks was an incredibly effective strategy, even if it was ridiculously expensive. And this brings us to the perfect cliffhanger for our next session. VGG clearly demonstrated that depth is power, but it achieved this through a brute force trade-off, sacrificing efficiency for simplicity. This raises the critical question that drove the next wave of innovation. What happens when you hit a memory or compute ceiling? How do you build networks that are even deeper and more powerful, but also significantly more efficient? That is the puzzle that architectures like Google Net and the revolutionary ResNet were designed to solve, and we'll explore their ingenious solutions next week.